Well, I'm so glad we're finally into the multivariate analysis regressions. We have been using multivariate all the time. I've been talking about omitted variable bias, which implicitly is about two variables all the time. So I'm really glad that we're finally here to understand some of the aspects of multivariate. So the first thing I want to do is to give a small introduction to understand how things change when you have two variables at the same time. And then we're going to look at some technicalities and then something that is called partially out. So we have 3 videos in this unit. Okay, so the first is that multivariate is extremely useful because it is very common that you have confounding effects. It's very common that you want to understand what is the impact of wages, of education and experience on wages. And it is an issue that education and experience are related to each other. So what we would like to do is to understand what is the impact of education alone on wages by keeping experience constant. The same with productivity of a company. How important are managers, how important is investment. So we would like to know the contribution of each variable independently. So we always will make statements like, I increase education, keeping everything else constant. And so that's a very typical notion of what we are going to do in a regression. And even though that actually is very natural, I just want to highlight that there are many instances in which that actually makes no sense. So for example, imagine you're running a regression on DSNP and there's a variable that is non-linear. So you have an impact of x and x squared. So, whatever that x is that okay? So let's assume that there's a non-linearity. Then increasing x and keeping x squared constant is kind of a complicated, mental exercise. So truly, you're not keeping the x2 constant. So we're going to learn a little bit about the impact of these variables when you have non-linearities. This is very important in machine learning. Machine learning, this notion of orthogonality, where you move one but not the other, is not that easy to understand. Let me construct a simple data set and show you the power of conditioning, which means controlling. So we're going to have two variables, x and z, and as always, you can see that we use the same type of framework to do all the simulations. So I'm going to have x and z, two variables. The z is going to be a dichotomous variable, 0 and 1. So, and it will be I will just create a random variable psi, whatever it is, and when that is positive, I will assign z to be 1, and when it's negative, I will assign that to be 0. So you can assume that that is ability or something like that. It can be the experiment, and so I want to relate this to also to the randomized control trials that we did before. Okay, so we are going to assume that beta is negative, and so these are small changes, and that's why I put them separately. But the beta is going to be less than 0, it's going to be -1. The gamma is going to be 5. If x and z are positively correlated, we know that the beta hat will be the true beta plus the gamma times some alpha, and that alpha will be the correlation between x and z. So if alpha is positive and gamma is positive, it is conceivable that OLS give you a positive coefficient even though the true one is negative. And in fact, I'm going to choose an alpha to be positive, and this is it. So I will take x equal to alpha z, and the alpha is positive. So we know that the bias is going to be upward. Let's see more or less what happens when we simulate and run this regression. These are the data points. These are all the z's of 0, and these are all the z's of 1, okay? And now, the slope is positive. We expected that because the bias on the alpha and the gamma is so big that it's pushing the regression to have a positive slope, okay? So, and not surprising, the coefficient is positive. So if we run the regression y on alpha plus beta x, that beta is 0.7, okay? So it's positive. So we omit z and we will have a bias. What is truly happening is that if you look at the data only conditioning on the z, so when the z is equal to, and by the way, you can do this because z is 0 and 1, so I have done this just for simplicity. If z is a continuous variable, this is much harder to do. But if c is 0, 1, if we look at the variable only with c equal to 0, well, that slope is actually negative. And when you look at the z is equal to 1, that slope is equal to, is also negative. The issue here is that because the z are correlated with the x, that is what is pushing the cloud of points to be, the cloud of points will look positively correlated. The Simpson's paradox is that one, is that if you compute the correlation in the whole population, you get a positive number, and if you condition on gender, then you get a negative number. If we run a regression where we condition, where we actually run y equal beta x plus gamma z, I'm forgetting about the constant just for a second, then notice the beta is equal to -1 and the gamma is equal to 5. So we recover the two parameters. There's something that we are going to call partialing out. There's a way to run this regression in steps, okay? And what we tend to do is that we look at the orthogonal component of x and z. So what we're going to do is say, well, x and z are correlated. So I'm going to construct a new x. So let me call ort. And this is the component of x that is orthogonal to z. So x will be x orthogonal plus x not orthogonal. And the x orthogonal is, independent of z. But the other one is correlated. So we're going to construct that, and this is called residualizing. So if I take, if I compute the residuals of x, and I run a regression, so I clean up all the impact that z has on x, this is the new data, how it looks like, and now you can see that the two slopes are identical. If you perform the same residualizing on the y's, actually then the two lines will be completely aligned. So the regression, the multivariate regression, what it's going to do is that it's going to take that component of x that is, when you control for the z, is that okay? Is you're going to take that component of x and y that are explained by z, you're going to take that out, and then the impact of x on y will be perfectly seen. And you can see here that the two data sets are centered with each other, and in fact the slopes are identical. And if you run the regressions, you do that. So this is the regression, sorry, this is not both regression, this is the run regression. This is when I only have only x. Okay? And this is when I actually compute the residuals. I computed this orthogonal component, it's called partialing out. Look, we get the correct coefficient, and when we partial both out, you get the exact same correct coefficient. Okay? So it is remarkable how this works, and what I want to do is to explain with a little bit of algebra how does the OLS regression separate all these components. Okay? See you in the next video.